professor of Microbiology at the University of Birmingham, and he's had long-standing interest in a number of areas related to bacterial pathogenesis, but specifically today he's going to talk about some high-throughput approaches to studying the genetic epidemiology of gram-negative pathogens.
Great. Thank you for the invitation to talk. So I'm probably going to try and squeeze a quart into a pint pot, but here goes with just half an hour. Let's start with the state we're in. In terms of diagnostic microbiology, particularly bacteriology, we're now in the 21st century, but most of the time we're relying on 19th century techniques. Microscopy and culture on solid media date from the time of Koch and Pasteur. And I think it's perhaps time we should think about doing things a bit differently and perhaps a bit better. Now, I'm very mindful of the fact that this is funded by the federal government, and it's very important to declare potential conflicts of interest at such meetings. It's very good that Arturo has introduced the idea of philosophy and religion. I have to declare allegiance to a particular belief system, and this belief system is summarised here in this Wikipedia article. It's a belief system known as genomic fundamentalism. And I'll just very briefly talk you through this. It's a belief that the world was created by Lord Venter on July the 28th, 1995. And any appearance in the world of an existence before that was there just to test the faithful. We have our own particular creed, genomic creed. There shall be one diagnostic test, and that is whole genome sequencing. We look forward to the imminent arrival of what we call the sequencing singularity, when sequencing becomes cheap enough to replace all other tests. We venerate various deities. The Dark Lord Vader of Sargasso is the latest and final avatar of Lord Venter, and there are others listed there. I'm not going to go through them all in detail. There are various break-off branches, the Genites and the Clarites, Sisterhood, and so forth. There are the old order genomic fundamentalists who posit that the world did actually exist before Lord Venter's Fiat Genoma Declaration, and they venerate the pre-Venterite Brotherhood, Lord Stanley of Bitterroot and Lord Relman of Stamford as early prophetic forefathers. And in our paramilitary or jihadi wing, called Sequence First or Just Sequence, there's been extensive military activity in the so-called shoe leather wars, fighting shoe leather epidemiologists. And their slogan there is, "Our sequence will come." And finally there, just to underline our kind of credentials there, we have an unofficial anthem, a nerdcore track called "Just Sequence the Shit." Just sorry for the profanity, but that's the nature of hip-hop. Anyway, moving on more seriously, what about sequencing in Birmingham, where I come from? We're not really a large sequencing centre like the Sanger or other centres like that. If you like, we're more like GarageBand than say the Rolling Stones or Pink Floyd. But doing sequencing in a garage, we can get a lot done. You can see our kind of nerdy credentials here. Nick Lohman blogging about how he was like a kid waiting for Santa Claus when waiting for our first sequencer to arrive, our 454. You can see it here arriving in a crate with my colleague Charles Penn looking a bit of a lemon standing next to it. Since then, we've got an iron tolerant and a MySeq as well. Now, what I'm going to study first, talk about first of all, and rather quickly, I'm afraid, is Acinetobacter baumannii. And this is our first case study. This is a gram-negative bacillus. It's multi-drug resistant, usually. Colistin and tigecycline remain in many cases as reserve agents, but even there, we are sometimes seeing a movement towards pan-resistance, where there are no available agents left. It's associated with wound infections and ventilator-associated pneumonia. Sometimes finds its way into the bloodstream as well to cause bloodstream infections. And it's particularly gained notoriety in returning military personnel from Iraq and Afghanistan. And at one stage it was called the Iraqi Bacter. And there have been cases of transmission from military to civilian patients in shared healthcare facilities. So what we were interested in were a number of questions. So could we actually apply whole genome sequencing to Acinetobacter isolates to detect differences between isolates within an outbreak? And then could we use those differences to determine chains of transmission? That was our first question. The first two questions. The third question was, can we actually see resistance emerging? How can we see what the molecular mechanism for that is? And then finally, can we use genomic methods in terms of taxonomy and identification? So starting with our outbreak, we had an outbreak in a Birmingham hospital in 2008, and all the isolates within that outbreak were classified as indistinguishable by all the current typing methods that were used by the reference laboratory. Things like VNTRs and sequence-based typing and so forth. Well, to cut a long story short, we actually sequenced the whole genome of 6 isolates from this outbreak, and we searched through those genomes for SNPs, and we found that there were 3 SNPs that varied, 3 loci in which there were SNPs that varied between those isolates. And we came up with a genotyping scheme that involved those 3 SNPs. And they were all validated by Sanger sequencing as well as high-throughput sequencing. And as I say, I'm having to rush through this. To cut a long story short, we ended up with a picture looking like this. This was how those genotypes mapped onto the time and space aspects of the outbreak. So we had 4 patients in one 6-bedded unit within the intensive care unit, 1 out on the main intensive care unit, and 1 out on the trauma unit. And if you look here, you can see that there are identical genotypes in 3 patients here, M2, C2, and M4. And as M2 and C2 were in adjacent beds for a period of time, we made, on the basis of the genotyping and the extra contextual data, the assumption, the conclusion that there had been cross-infection between M2 and C2. Now, those of you who are still awake will say, well, hang on, you haven't explained M4. Well, actually, M4 and M2 are both military patients who were both repatriated to the hospital through exactly the same care pathways from Afghanistan. And so our assumption is that they both acquired their infection from a common source before they arrived in the hospital. Now, you may also be saying, well, isn't this rather a sledgehammer to crack a nut to actually do all this genome sequencing just to tell us that 2 patients in adjacent beds, one infected the other? Well, at the outset of this, we had no idea whether we'd find any SNPs, whether we'd find thousands of SNPs or a few SNPs. We had no idea whether we'd be able to make any inferences at all. So we were quite encouraged by these findings when we actually put all this together. In terms of antibiotics, we then went on to a study in collaboration with colleagues in London, looking at isolates from a patient who received tigecycline therapy. Before the therapy, the Acinetobacter baumannii the patient was carrying was sensitive. Afterwards, it had become resistant. And so we compared the isolates before and after, and we found 18 SNPs this time, a rather larger number of SNPs than we'd seen in our previous study. 9 of them were non-synonymous, and 1 of them was actually in a gene called ADES, which is known to be part of a pair of genes that encode a 2-component regulatory system, which is known to be involved in resistance in this particular pathogen to that particular agent. So it was very nice that we actually found a plausible explanation for the resistance. But one thing we found that was counterintuitive was that actually there were 3 contigs in the earlier isolate that were not found in the later isolate. And most of us assume that when you get resistance, it's because you've got something new, you've got something extra come in. But what seemed to have happened here is that in moving towards resistance, there'd actually been loss of DNA. And one of those pieces of DNA that was lost actually truncated a gene called MUT-S, which is involved in DNA repair. And our interpretation of this is that loss of DNA repair in this lineage through the truncation of that MUT-S gene led to an increase in the mutation rate and primed that lineage to then acquire the antibiotic resistance. And similar things happen in other contexts, for example, in the evolution of cancers when they become resistant to chemotherapy and so on. Again, I'm rushing through a lot of stuff very quickly. The 2 previous studies have been published. This study here on the phylogenomics of species within the genus Acinetobacter is currently under review in PNAS, and we're waiting with bated breath to see what they make of it. What we did was we sequenced 13 new isolates to get 13 new draft genome sequences representing 10 species within this genus. It's rather difficult to demarcate species within the genus by phenotypic methods alone. We then scooped up all the other Acinetobacter genomes that we could find in the public domain and analysed them all together, and came to the conclusion that if we look at 16S sequences, which are commonly used as a molecular barcode, as a taxonomic marker, they were pretty hopeless at delineating the accepted species within the genus. But what we found is if we did a core genome phylogenetic tree, we found that was consistent with the currently accepted taxonomy. It did actually identify 3 misclassifications within strains from strain collections, which we are fairly robust are actually misclassifications. Doing phylogenetics like this, though, is actually quite processor intensive and takes a lot of time, and we were looking for a quick way of delineating species as well, and we found that it's not a technique we invented, it was already published, but using average nucleotide identities quickly delivered results that were consistent with the traditional and phylogenetic classifications. Now, speaking after Eric Alm, I'm conscious of the fact that I'm not going to try and defend any definition of species or any of the bacterial taxonomy that goes on. It's rather like teenage sex. Bacterial taxonomies define species at the moment, and we have to live with what they do, and that's what we did here. We actually found that we could find methods that mapped onto the existing designations that are out there. And rather provocatively, we are speculating that we could actually move towards a system where you define species by genome sequence alone and don't have to do any phenotypic testing or any other onerous methods like DNA hybridization to define species. We'll see what the PNAS reviewers make of that one when we get the reviews in the next few days or weeks. Right, I'd now like to move on to case study number 2, which is on the German E. coli 0104H4 outbreak, which David Rasko mentioned yesterday and laid some of the foundation for. So this outbreak was active just over a year ago at its peak. Over 4,000 cases, over 50 deaths now, in fact. Mainly centred on northern Germany, but cases were scattered throughout Germany, and there were cases in individuals in other countries who had been to Germany and then returned home to their home countries. It was linked to sprouting seeds. It was characterised by a very high risk of hemolytic uremic syndrome, a particularly nasty complication of sugar toxin producing E. coli's. And for some reason, as yet unexplained, females were particularly at risk. My favourite explanation is that real men don't eat bean sprouts, but that may or may not be the acceptable explanation. So what did we do with this? Well, what happened was that our collaborators in Hamburg actually had contacts with BGI in Shenzhen and sent an isolate to BGI in Shenzhen, or some DNA from an isolate, and BGI had just acquired an iron torrent and thought, oh, well, let's just have a play with our iron torrent, and they sequenced it on the iron torrent. We had just acquired an iron torrent as well, and this guy here, Nick Lohman, who you've heard about before, was playing around with doing assemblies of iron torrent data and had worked out how to do that, and happened to be at the bioinformatics conference just as the BGI data was released into the public domain. A very inspired thing that the BGI did, actually, releasing their data straight away into the public domain. He picked it up and then assembled it and then did this blog post here and then tweeted on it to say, well, hang on, why don't we all as bioinformaticians just grab hold of this data and see what we can make of it? And he kick-started it by doing this assembly. Well, within 24 hours of its release, he'd assembled the data, but within 2 days, it had been assigned to an existing lineage. Within 5 days, analyses had given rise to a strain-specific diagnostic test. And within a week, the bioinformatics community had taken this up, and there were over 24 reports on the biology and evolution of the strain filed on an open-source wiki. This screen dump here just gives you a feel for the tremendous activity that went on. You probably can't quite read it, but if you just look at the names there, you can see the variety of input here. You've got English names, Spanish names, Chinese names, you've got Muslim names, Jewish names. People from all around the world are actually, from multiple continents, were actually involved in this activity. And none of them were professional health, public health people, for the most part at least. They were people just doing this out of interest and goodwill. and as part of the fun that was going on at the time, if you like, the excitement of it all, and also because there was a clear and present need for it. Now, actually, as it happened, I was away on vacation when this kicked off, and I came back and Nick was explaining it all to me and getting very excited. And I said, hang on, we work in an academic institution, and a few tweets and a blog post do not equate to a peer-reviewed research publication, and that's what we have to do in academic life. We can't just piss around tweeting all day long. We have to write papers and grant proposals. And he said, why do you have to be such a grumpy old man? Don't you pick up on the excitement of this? As it happened, we managed to actually get in contact with the Germans and with our Chinese collaborators. And I still kind of pinch myself that we managed to actually package all this up, square the circle, and actually turn it into a peer-reviewed publication in the New England Journal of Medicine. We wrote up a case study of a family outbreak. I concentrated in the narrative of the paper on the journey, on the actual fact that we had all this tweeting and blogging and community effort. And for consistency, we made sure that we repeated all of the analyses that we were reporting. Nick did that in-house to be certain of it all. What were the takeaway messages from all this? Well, Germany is one of the most advanced societies on the planet, and it was devastated by infection. So I think it was an American Attorney General, was it, or someone who said a few years ago, it's time to close the book on infection. Well, infection's still there and it's still a threat. Pathogens don't bother with passports. It's clear that this was not a new strain. Firstly, people say, oh, it's a new strain, something completely new. But a guy called Mike the Mad Biologist, who's a blogger from this side of the Atlantic, pointed out it wasn't, something that's been seen in Germany 10 years before, very similar. And in fact, the closest genome sequence strain was actually from the Central African Republic in the 1990s and belonged to an enteroagglutinative lineage. So for people that like to pigeonhole things, this was something of an issue because it was initially, as Dave Rasco pointed out, it was called enterohemorrhagic, and then it turns out it's not, it's enteroagglutinative. And some people tried to mash the words together, and there are umpteen different names given to this. Let's just be neutral and call it German STEC, but it came from a lineage anyway that circulates in human populations. So enteroagglutinative E. coli, there's not any clear link to animals, whereas with traditional EHEC, things like E. coli 0157, basically you're looking for cow manure getting into the human food chain somehow or other, or into human mouths somehow, whereas that wasn't necessarily the case here. And there are all sorts of things going on in terms of virulence factors moving into the lineage. Obviously, the sugar toxin gene coming in on a phage into this lineage, other mobile genetic elements. It's clear that our attempts to try and catalogue things and be very hierarchical about the way we look at stuff doesn't always work, and that pathotypes evolve and overlap. And another rather unnerving feature of this was that this organism had an extended spectrum beta-lactamase, even though we don't give such agents to treat diarrhea in this kind of setting. It can kind of primed with antibiotic resistance, which is a rather unpleasant thing. In terms of the kind of, sociology of science, if you like, we coined this term open source genomics as a propitious confluence here of high throughput genomics, crowdsourced analyses, with a liberal approach to data release, actually putting that data out there as quickly as you get it and your analyses as quickly as you get them. And I think we did establish the point that social media such as blogging and Twitter can augment the usual channels of academic discourse. Of course, it's worth saying we're not the first. I have to stress that there have been many other crowdsourced science projects. Jennifer Gardy has actually spoken about this at a TEDx talk where she talked about what happened with pandemic flu. And in fact, we were very guided by Jennifer's thoughts on this and mindful of her presentation when we were writing the paper. The other question is, have we actually broken the mold? Is this the way science is going to be done in the future, that there won't be all these closed lab books and stuff, everyone will just be sharing everything all the time? I suspect probably not. When you're dealing with a public health emergency, I think people will perhaps move in this direction, but I guess ordinary science will still be rather kind of closed door, closed mind type stuff. The other interesting question is that the New England Journal of Medicine used to have an editor called Inglefinger, who invented the Inglefinger rule, which was that you're not allowed to publish anything in the New England Journal of Medicine if you've published it elsewhere before. Well, all of this stuff had been put into the public domain through Twitter and blogs and so forth, but nonetheless, the New England Journal took the paper. So have we shown the finger to Inglefinger? I'm not sure whether we have or not. Just in the last few minutes, I'd like to also now move on to some discussion of benchtop sequencers. So this has been an interesting development in the last year or so, where sequencers have become much smaller and much handier and much cheaper, and they just fit onto a benchtop now like a kind of glorified laser printer, and this opens up lots of new opportunities, particularly for labs like ours that kind of run out of a garage when we're not a large sequencing centre with lots and lots of money and resources. Time is short, so I'll just put up a screen dump from our recent paper where what we did was we took a British isolate from that German E. coli outbreak, and we sequenced it on 3 different platforms. We didn't do all of the work ourselves. We did this in collaboration with our colleagues at the Health Protection Agency. But we basically sequenced the same isolate on the 454 GS Junior, on the MySeq, and on the Ion Torrent PGM. To cut a long story short, we did not find didn't find any of the platforms to be self-evidently the platform that you must buy, and none of them were so dreadful you'd never use them again. They were all, in a sense, fit for purpose, and they provided genome-level information. We did highlight some of the issues that perhaps those in the know already knew about, which is that the Ion Torrent and the 454 do have problems with homopolymers, and in fact the Ion Torrent seems to have worse problems with homopolymers than the 454. This was published about 3 or 4 weeks ago in Nature Biotechnology. As a microbiologist, I'm not so interested in all the technicalities. Nick Lohman has detailed all those in the paper. But what I said is, what does this actually tell us about the biology of the organism if we use these different sequencing approaches? It's also important to remember it's not just the sequencer you use, it's the analytical pipelines, and particularly the assemblers that you use to do the assembly. And Nick tabulated all this here, and basically what you find is that none of these sequencing platforms gives you perfect results. We looked at a variety of genes that we thought were of biological interest in these organisms and saw if we could capture those genes, the full length of the sequence of those genes, using these various approaches. And you can see that it varies according to which approach you use. But even with the best approaches, say where you're using MySeq and CLC, you don't get everything perfect. So there are these things called SPATEs, as kind of auto-transporter genes that are very long and a bit repetitive. And even with the best assemblies, we did not get those genes in one fragment. So in the last couple of slides, what about moving towards microbiology 2.0, where we don't bother with culturing, we don't bother with microscopy, we just go from the shit to the sequence? How are we going to do that? Well, in collaboration with our German colleagues, we actually got we started what we call the German Shit Project. And they have sent us DNA from fecal samples from patients in that outbreak. In this first experiment we did, we looked in run 1 at a patient who had the STEC in large numbers in their stool by conventional culture. And in run 2 we looked at a patient who had diarrhea around the same time, but in fact didn't have the STEC but had Salmonella enteritidis infection instead. And this is what we found. I think these are our very first runs on the MySeq, which we got a month or 2 ago. And we were fairly pleased with the results. In fact, the first run, we didn't get a read in one direction. We only got it in one direction instead of about 2. So that was a little bit disappointing. We got about half the data we expected to get. But nonetheless, it was useful to us. And interestingly, we looked at the data. Nick screened out anything that matched the human genome. And he found that in the first sample, there was a lot more human genome than there was in the second sample. So presumably, that is tissue damage, stuff sloughing off into the feces, and the liberation of human DNA. This is all very preliminary stuff, so Nick has actually done an alignment of the reads from that sample to the E. coli 0104 from the outbreak, and shown that basically he's getting about 10-fold coverage on average of that genome. So this was actually quite encouraging. It basically suggests to us that there is a good chance that you will be able to recover this kind of genomic level data without subculturing from the samples, without doing amplification or capture or anything like that, just sequencing the fecal sample. And interesting here also, there was a little peak there you can see where when you align against the sugar toxin phage, and this actually makes biological sense in that we know that the toxin is actually released during the process of lysis, and we would imagine that lysis was going on in this fecal sample, and therefore there would be a greater abundance of the phage genome than there would be of the background genome. Nick tried to then do the same kind of thing with the Salmonella enterica genome, and here he found a much more complex picture, all sorts of organisms in there, when he just tried to do a very quick and dirty alignment and a sort of binning against various taxa. So in the E. coli sample, very simple, lots and lots of E. coli, lots and lots of human genome, and less of other things, whereas this is much more like a traditional fecal microbiome. And in fact, it's clear when you look at this that there are lots of difficulties in actually working out what's in a sample, because when you use these kind of approaches, it tells you that 1% of your reads are aligning against Shigella, when in fact we know there's no Shigella in there. Those are just E. coli's. It just happens that occasionally the algorithms pull up the highest scoring hits to Shigella rather than to E. coli. So it's all nonsense, and we can't interpret this. And in fact, the Salmonella reads are in there, but they're in this 31 more in the Enterobacteriaceae there. So we have not yet actually dug them all out and worked out exactly how much we can recover of that genome. But nonetheless, this very study we've only been done in the last 2-3 weeks is giving us hope that we can actually go straight from the sample to recovering pathogen genome level information. So to close, we've got many opportunities ahead of us here. Genome sequencing does bring the advantages of open-endedness, revealing what your guy Rumsfeld called the unknown unknowns. You don't have to devise PCR primers or probes, you just find out what's in there. It's got universal applicability, the ultimate in resolution, as Jennifer pointed out. Benchtop sequencers are coming in now and poised to revolutionize microbiology. The platforms do have strengths and weaknesses. None of them is ideal. We haven't reached the sequencing singularity yet, but you know, we ain't seen nothing yet because we're all waiting. It's a bit like the kind of South Seas cargo cults. We're all waiting for an aeroplane to arrive that will deliver the cargo of the Oxford nanopore in our laboratories, because there's been a huge amount of hype about this particular platform where you have a neat little USB stick which you plug into your computer and it will stream the data into your computer in real time. It just sounds too good to be true, but if it is true, it's going to revolutionize the landscape even more. Oops, that shouldn't be there, that shouldn't be there. So there are some challenges. It's not all, I wouldn't want to be simplistic. Genotype does not always easily predict phenotype. There are heterogeneities in pathogen populations. So when we do genomic epidemiology on single colony isolates, we may be fooling ourselves. And we're going to hear more about the Amerithrax investigation later, where looking at heterogeneity in the population at levels that are below what we would currently see when we just sequence a mixture of, sequence a sweep of the colonies, that still is able to reveal interesting things about the populations. It may be that some bacteria do evolve so slowly that we cannot actually infer any transmission chains down at that level of patient to patient. Maybe indistinguishable really does mean identical. Sequencing a genome means different things on different platforms. That's been said before, and it's going to be said a bit later as well. And my own discipline of clinical microbiology is a very conservative discipline, and there is this question, how are we going to move from what I've now run away from the clinical microbiology lab, and I live in an ivory tower. How am I actually going to communicate anything back to the real world out there? And how are we going to communicate with clinicians, busy clinicians? It's also worth pointing out that even if high-throughput sequencing does get adopted in clinical microbiology, it probably doesn't mean that we're going to get rid of microscopes and agar plates. I mean, radio has survived alongside TV as an alternative medium, and who knows where we'll be in 10 or 20 or 30 years' time. So what I'd like to say is that, in a sense, the promised land is in sight. Here's Moses here looking at the promised land of sequences, you know, coming out of those samples readily and easily. But in fact, there's still many rivers to cross. We're not quite there yet. We get a glimpse of it. And we made these points as a paper, opinion piece we wrote for Genome Medicine, which covers some of these points a few months ago. That's me finished. I'd just like to, if anyone wants to read more about what we do, you can look at our blog and Twitter feeds. I should be putting this talk up onto YouTube, which should be available this afternoon if anyone wants to listen to it all again. If anyone wants to come and work with us in Birmingham, we have, for early investigators, we have a scheme called Birmingham Fellowships. If you just Google that, you may be able to apply for that and then come and work with us. We've been tweeting, several of us, on this particular workshop with the hashtag of SAMG12. And I've just left there a quote from the Lunar Society of Birmingham, from Joseph Priestley, who used to live in Birmingham until the people of Birmingham drove him out and he came over here and lived in America. But he made this point about the Lunar Society of Birmingham, that we were united by a common love of science. And this, I think, talks to the idea of crowdsourcing and putting this stuff out to the world. And then I'll just put up an acknowledgement slide, but I'm not going to read any of that out. I'll finish here. Thank you. We've got what David Relman finds in pox viruses, stunned silence. Eh?
You'd think I'd ask about E. coli, but I'm actually going to ask about Acinetobacter. In the grand scheme of things, we have all of these isolates from hospitals and from patients that are coming back from the Middle East. Is there any idea of the prevalence of Acinetobacter in the population of people just walking on the street in Birmingham? And are those isolates significantly different from the isolates that you're finding in the patients in the hospital?
We haven't actually done any surveys of patients in Birmingham. In stool samples or skin or anywhere like that. So I wouldn't be able to answer that one. I mean, people are doing those kind of things for extended spectrum beta-lactamases. There seems to be a lot of traffic in those kind of genes coming from the Indian subcontinent back to Birmingham when people go there. But we haven't done it. I mean, the thing is, it doesn't tend to, I mean, if you take the general population of the hospital, which, many of those people are in there for all sorts of reasons, you are kind of sampling the population. We don't tend to see Acinetobacter in that setting. If someone comes in for a routine operation, we don't isolate it. It tends to be in these very particular settings, multi-drug therapy, critically ill patients, that kind of thing.
Mark, I think you made an important point. The genotype doesn't always map to phenotype, and I'm just curious about your thoughts on whether you think that is more driven today by a lack of understanding of fundamental biology, or more to the point that you made, that we have multiple platforms with multiple limitations, multiple assembly algorithms, and it's very hard with all of those options to really be working to do assembly and annotation based on some truth, because that truth is very elusive.
Yeah, I mean, I guess I am a positivist. I believe the truth is out there. But you're right, in terms of the methodological approaches we have at the moment, we are not getting perfect truth. And we are also concentrating on the low-hanging fruit. So there's a lot of interest in SNPs. But there are other changes in the genome which are not as easy to find, which we just ignore. I mean, Julian will tell you about in Yersinia pestis, all those rearrangements that go on in real time and so on that would be opaque to us using most of these approaches now. So yeah, we've got a long way to go, and it's just the start of the journey. And we're all in a kind of just running as fast as we can to keep still, to keep up with the technologies. I mean, much of the effort we're putting in now into making, say, short reads work for us probably will become redundant when we get the ultimate long read technology. I mean, Jack Gilbert made this point at a meeting I went to a while ago. You know, we're just waiting for that, effectively, for that sequencing singularity when we do get long read technologies that are accurate enough to give us genome-level assemblies cheaply and easily. But we'll get there. The promised land is in sight.
So, Mark, one of the things that I think could be helpful in dealing with the valley or the sea before promised land is to address head-on where there may be unmet expectations by consumers of interest, say the clinical microbiologists. What is it that they believe has value in terms of information gained in the clinical microbiology lab that may or may not be met today by this substitute form of information, genomic information, and then take those phenotypes of interest and really address in a quantitative fashion how much can we say about this and that now today, although it may change, and how much not, and that may even be a driver to them to say, look, these guys out there who are generating all this stuff that they said would tell us everything, admit that today they can only tell us this much, which means that it's up to us to recover the isolate and do the other part, because it's going to otherwise fall right through the big, crack of the sea, the gap in the ocean. Comment?
Yeah, I think we have to be realistic about not overselling the technology and recognise that we're not quite there yet. In fact, if you adopt a kind of Cartesian doubt about the utility of these technologies, you can apply that also to the whole of microbiology. And you could argue that, in fact, what did the microbiology tell us? Did the microbiology save any lives in the German E. coli outbreak? It was the traditional shoe leather epidemiologists who actually discovered it was the bean sprouts. But even then, discovering it was the bean sprouts didn't save any lives because they found that out after the outbreak had finished anyway. And so you're right, actually getting a setting in which this makes a clear and present difference to patient management, patient outcome, is the challenge, and there will be some settings where that will probably be fairly straightforward. And we spoke last night about cystic fibrosis patients, acute exacerbations, often there's not an obvious cause, the microbiology doesn't correlate with the clinical. In situations like that we might discover that they do have a virus on board that we didn't recognise, or that they have another bacterium that we didn't see before, and that may help guide management. Similarly with the chains of transmission, if patients are acquiring Pseudomonas aeruginosa, where are they getting it from? Those kind of things I think we can start to say, well, actually we can see where this is happening. It's clear that the transmission is happening in the hospital or in the healthcare environment, or it's happening socially or whatever, and we can then guide management. But you're right, it's very difficult to predict how things are going to look and how this is all going to bed down. And in the past I have been told that you molecular people made all these claims about PCR 20 years ago, and that PCR would get rid of agar plates and all this stuff, and it hasn't. I mean, it's got some uses, and the virologists have obviously made much use of PCR, but bacteriologists are still wedded to the traditional 19th century approaches. Okay.
Thank you. Our final speaker